Good evening, everyone. Welcome to SLAC National Accelerator Lab. My name is Kelly Gaffney, and it is my pleasure to introduce tonight's speaker, Shuchang Zhang, who is a distinguished scientist and professor of physics here at the Stanford University and also a member of our SLAC Stanford community. Professor Zhang was born in China and had his formal education occur both in China at Fudan University, also in Germany at the Free University of Berlin, and also at Stony Brook in New York. But I think more interesting with regard to his career was the informal education he had before he entered university. So Professor Zhang was at the forefront of the intellectual reawakening that happened in China in the late 70s and early 80s. And because of this, in his early years, he was self-taught to a great extent. And I think that this may be a piece of why his scientific career is distinguished from many others, which is distinguished in large part by his creativity. So with that, I hope that that will be expressed in tonight's talk, and I hope you enjoy it.
So, thank you very much. It is indeed a great pleasure for me to share this wonderful evening with you today. Actually, I'm keenly aware of who my competition is. Before I came in here, I turned on the TV and I was so shocked. I was sure that no one would come to my talk. Because, but it looks like today, most of you are more keenly aware of interested in the state of the universe rather than the state of the union. So, I have been a professor at Stanford for 20 years. This is my first time I'm doing this. So this is indeed a great pleasure. And I hope that all of you can feel quite relaxed and we share this evening in a relaxed pace so that we can understand and so that I can share with you some of the exciting development in basic science. But usually, some of the interest in basic science concerns the far corners of the deep universe. But the topic today is actually very much at the center point of the prosperity of our Silicon Valley, our very home today. So I'm sure that many of you have seen this graph many, many times. Actually, to a distinguished audience like we have here today, I'm sure that some of you may even have contributed to this so-called Moore's law. So this is the law, kind of a law of economics and a law in the information age, which is responsible for the tremendous progress of the information age and also responsible for the prosperity of the United States and very much so of the Silicon Valley. So it basically was stated by Gordon Moore in the 60s. He observed that the number of transistors on a semiconductor chip, when you really take your computer apart, you kind of see that the size of your semiconductor chip basically doesn't change very much. It's almost always a postage stamp size. But the number of transistors inside this chip doubles every 18 months. So this is a remarkable, remarkable phenomenon. Actually, ever since the human civilization, there has never been an industry that could innovate at such a rapid and exponentially growing pace. So you observe that here is the number of years since he formulated, maybe he formulated even back then in the 60s, but here is what we call a logarithmic scale. So here we don't go from 1,000 to 2,000 and to 3,000, but we add a zero every time we go up in the vertical axis, counting the number of transistors on a semiconductor chip. And this is basically what is responsible for the tremendous progress, things that we take for granted, that the iPhone today had the power of IBM mainframe computer of yesterday. So this is the thing that we have taken for granted, but there's every indication today that this law, this magic law of progress, of exponential explosion of the information age is coming to a standstill. It's basically facing some fundamental crisis that we will, if we go on in the regular paradigm of doing things as usual, we will not be able to keep up with this rapid progress. And that will be really sad, both for Silicon Valley, for the progress of the information age, and so on. So the story I would like to tell you today is how scientists are coming. Actually, when Gordon Moore first formulated this law, it was a moment, a starting point of a tremendous chapter of progress in human society. But to a certain extent, it was also a sad moment when science and technology parted on their own way. Because the relentless pursuit of the Moore's law in the past 60 years mostly was due to technological innovation, not that much to do with basic science. But now we're facing such a crisis of such a magnitude that we have to rethink at a very basic scientific level how we can do things better so that we can keep the Moore's law from saving the Moore's law so that it can always keep on going. So in order to understand what's the problem and what was the progress and what's the problem we're facing now today, let me go back to the very basics of the most basic building blocks of the information age. So the information age can be reduced, the basic building block, to two elementary particles. One is the photon, which is the carrier of the light, and the other is the electron, which is the carrier of the basic logic processing inside a semiconductor chip. So basically, electrons process the information and photons transmit this information. The reason why we give these two elementary particles two very different roles is because they have very, very drastically different properties. Photons basically interact with each other very, very weakly. If you're in a vacuum, if two photons meet, they don't even talk to each other. They don't notice each other's presence. So it's this very remarkable property of the photon, which is actually responsible for how we carry information at a very fast rate over very, very large distance. For example, there was a Nobel Prize awarded to Charles Gall for fiber optical communication. Inside these optical fibers, it's all these photons which are zooming around and going from San Francisco to New York in a split second, but this is all due to the fact that we can pack many, many photons into this fiber optical cable, and they barely interfere with each other. They are not so perturbed or disturbed by their surroundings, by the obstacles, and as a result, they can carry information without much attenuation. So this is the magic property of the photon, one of the elementary particles that we have. The other is the electron, or familiar object, electrons. When you take an atom apart, there's the electron which goes around the atomic nucleus. Now the electrons has totally the opposite property. It interacts with each other very, very strongly. So basically they repel each other. If you have the two electrons which carry the same charge, as you pack them, as the distance gets closer and closer and closer, they repel each other by a tremendous amount. It is this interaction, this very strong interaction, which gives us the possibility to construct basic logic processing units. Because if I put some electron here, I can perturb the other electron on purpose so that I can construct a gate that switches on and off and on and off. And out of this switch, we can construct computing chips. Now, it turns out that this very strong interacting nature of the electron is a double-edged sword. And a lot of you are already feeling it now. You all have this annoying experience that as you put laptop on your lap, it feels burning hot. And when you use your cell phones, it goes out of battery very, very quickly. And the basic reason is the very same reason why we have Moore's law. Because over the past 60 years, the basic design of a semiconductor chip did not change very much. So roughly speaking, per transistor, it dissipates roughly the same amount of heat. Now, if the number of transistors is increasing exponentially, so with the heat, it dissipates, and it will go up exponentially. And this is the curve which plots how much heat it is generated by the intense operation of the electrons inside. So this is actually the problem. This is the most serious roadblock towards the Moore's law. That basically there's no way, so the amount of heat is generated so much that we cannot suck the heat out of the semiconductor enough so that to keep the chip from normal operation. So if we examine exactly why it is so that electrons are causing so much heat, we have to go to the very basic, go to deep inside a semiconductor chip and find what exactly are the electrons doing. Basically, the electrons are moving like this. So we already said the electrons have this wonderful property that they interact with each other strongly. Therefore, we can control them. We can construct logic gate and so on and so forth. But they also, as we pack these electrons closer and closer and closer in this relentless pursuit of the progress of the Moore's law, we're getting to the situation that the electrons are like cars moving in a crowded marketplace. They bump into each other, they bump into impurities, so the energy that we put into them by passing a current get quickly dissipated into their surroundings. So it's literally like that the electrons are moving. So this really looks like a very sad state of affair, that when you go inside, we all talk about this wonderful idea of an information superhighway. We indeed have, using photons, can connect remote parts of the world with very little loss of information from one place to the other. But on the other hand, when we go to smaller and smaller units of the electrons, we get into this situation that the close packing causes this tremendous interference in a crowded place, which now the chip interior has become. So now you say, as a lot of times, scientific progress are made just by analogy. Well, you say, if this is the picture, what is the solution? I think all of you will immediately propose, what is the solution? The solution should be this, right? So we should build a highway system for the electrons deep inside the chip, at the very basic operational units of the semiconductor chip, so that the electrons have this principle that we take for granted in a normal traffic environment of a highway, namely, opposite moving traffic are spatially separated. This is the basic principle of a highway. And if this is the case, then the electrons on the right-hand side will keep on moving forward in a smooth traffic situation, and the electron moving towards you, that's why you see the headlight, completely on the other side of the lane. This way, they will completely avoid collisions with each other, they will avoid dissipation, they will avoid this random state of motion of the electrons. This is the holy grail that we search in science today, okay? And this is indeed the story that I would like to tell you about today. So this is indeed a moment of both crisis and opportunity. So in order to appreciate the magnitude of the significance of this kind of discovery, let's move back into the chapters of history when transistors were first invented. Of course, this picture on the left, I don't know whether any one of you all recognize him. This is William Shockley. He invented, together with Bardeen, at AT&T Bell Labs back in New Jersey, the basic transistor. And they were awarded the Nobel Prize. It was a very important and significant discovery in basic science. But then, for family reasons, he needed to move back to California. He was a local boy here. And Stanford University was quick to seize this opportunity. He came to the physics department at Stanford, and he was both doing basic science, but also had the idea, wonderful idea, that why not turn this piece of basic science into technology as to change the way we process information, because back then we were processing information using vacuum tubes. And this was what happened when he first came into Stanford, and this is Silicon Valley now. So all the progress that we have today in Silicon Valley was due to this moment when science and technology met, at a crucial moment when a very important and basic idea met with practical applications, and following that with the relentless pursuit of semiconductor technology. So today, we're faced with a crisis. And as I said, that around the time when Gordon Moore formulated Moore's law, it was also the time when science and technology parted their way from each other. Technology was doing all of that. And basic science, and I will tell you a little bit about it, going to more esoteric and exotic phenomena into regions which are quite far away from technology. But today's crisis, as we face today, is actually a wonderful moment that offers us an opportunity for science and technologies to converge back again. So sometimes in English, this idea that crisis also means opportunity almost comes as an afterthought. But in some ancient language, this is deeply encoded. For example, in Chinese, when we refer Chinese words, phrases are made out of characters, and the word crisis is made out of two characters, and the first, believe it or not, the first character means crisis, and the second means opportunity. So these two are always deeply interlinked with each other in ancient culture with such a deep wisdom. Okay, so this is the exciting moment that we can think back into how we formulate and completely design the basic operation from scratch. And we already have a nice vision because we already see what the analogy could do because ever since the invention of the highway, how smooth our traffic system has become. So now, what is the science that's needed to realize such a dream? So that I like to tell you that in the basic science, there are two types of fundamental pursuits, okay? So ever since the time the Greeks formulated the idea of atom, there's one relentless pursuit to find smaller and smaller building blocks of matter. So for example, in chemistry, it was the search of new elements. After we discover enough elements, we formulate the periodic table, and then we look for all the possible elements. These are the smallest possible building blocks of matter at that time. But it turns out later that was not completely true, that there are elements are made out of atoms are made out of protons, neutrons, and electrons, and those particles in turn are made out of the subatomic particles. So this gives the golden age of particle physics, and historically, the SLAC laboratory was constructed for this type of pursuit to find ever smaller building blocks of matter. However, there's also another type of pursuit in science, which is best explained by a very simple phrase of how does complexity arises from simplicity. Okay? So we all have this experience that when we take the Legos, the basic building blocks of a Lego are very, very simple. But we can only marvel at the wonderful structures that our kids can construct out of these very basic building blocks. For example, in science, we have this phenomena that all of you know, that there's ice, water, and vapor. So they look very, very different. And they have very different, they're just very different. One solid, liquid, and gas. But if you break them apart into the smaller building blocks, they are the same H2O molecule. Okay? So that's the other type of science. One type of science is trying to find smaller and smaller building blocks. But now, after we find them, we look at the electron, we look at the proton. They're pretty simple. But how come is the world so complex? So there's another type of science which tries to understand how does complexity emerges from such a simplicity of the building block. And that is the science that I'm in. This is, can be referred to as the solid-state physics, or more generally, condensed matter physics, or material science. So for example, in the world of the electrons, they can form semiconductors, which are tremendously useful for all the information processing we do. We also have magnets that the electrons can, well, we discovered magnets very early on to use them as a compass, but today we can use magnetic properties as the basic storage units of information. We all face this tremendous problem of energy crisis, but there's a wonderful material called superconductors. And there, the electrons can carry current without any loss. But there's a little problem that it only works at relatively low temperature. So one part of the pursuit in my discipline is trying to find, for example, a superconductor that works at room temperature. And then you will really solve our energy crisis in a big way. But when you really take all of them apart, they're made out of the same protons. They're made out of the same electrons. So that's why there's another type of science that we try to understand how does the complexity of the world emerges from the simplicity of the building blocks. And so this is how different states of matter can emerge when you put these very simple building blocks together. And historically, actually, most of these materials were discovered accidentally. But after we discovered them, we learned how to use them. But today, as we face this problem that I just alluded to you today, that there's this tremendous crowding of the electrons deep inside of the chip, we try to find a way to build a highway system for the electrons. So we need a new organizational principle to put the electrons into this highway system. And this is the discovery I like to tell you about today. So it goes with an interesting name, and the name itself is quite suggestive. It's called topological insulator. Okay, so this topology, I will explain a little bit later, refers to a deep and profound mathematical concept. Insulator is a kind of a material, but basically, just to take away the picture, if you want to remember one picture, these are the materials where inside of them electrons move in a highway system. Okay. So the first material that's discovered is basically a very, very thin layer of semiconductor material, which is sandwiched. So when it is a few atomic layers thick, we can basically think of them as two-dimensional because the height doesn't matter. It's only a few atomic layers. So this is a piece of material. Its chemical composition is called Mercury telluride. And there, the electron really move like in a highway system. So this is only a few atomic layers thick. And in the deep interior of this flat two-dimensional world, electrons don't go at all. And the electron only carry a current along the edge. And it has this wonderful property that the upspin electron, and I will explain the spin a little bit later, move around in a clockwise fashion, and the downspin electron move around in a counterclockwise fashion. So this is the basic cartoon picture of what is this new material or the new discovery is about. It's called topological insulator, but as a picture, you see that the electron is exactly moving in a highway-like system where counter-moving traffic are spatially separated into different lanes so that they can move in a regular fashion. So a little bit later, there are also three-dimensional materials. So these are regular bulk materials, which has both a height and a linear dimension. And again, the electrons only move on the surface. They don't go to the interior parts of this material. So it's this material that gives us the wonderful control for align the electrons to move in this perfect highway system so that we can design the semiconductor chip completely from scratch and to completely and fundamentally solve the problem of dissipation as we face as a roadblock to Moore's law today. Okay? So now how does this happen? So let's imagine that we're driving a car on the highway. Let's imagine that the highway is very, very narrow, right? So if I drive a car and hit something, a lot of bad things can happen to me. My car can be dented, my window glass can be shattered into pieces, but actually not for the electron. Because the electron is already the smallest possible unit, right? You cannot imagine that the electron bump into something and be shattered into even smaller pieces. So when you try to think about if the electron is moving in a very, very narrow lane, like a very, very thin one-dimensional wire, then it can either move forward or it can move backwards. These two types of motion are still possible. You cannot break the electron because it's already the smallest unit. You cannot shatter the electron into pieces. But then when the electron hits some obstacle, the forward-moving electron will be hit back. And that backward scattering is the cause for resistance. So if the electron was happily moving around the wire, but we can never, as we go to smaller dimension, construct a perfect wire. And if it hits some impurity, and I told you the electron interact very strongly, then they will be immediately turned back. And that's how resistance occurs, because originally you put in this energy, you want the electron to move forward, but somehow they don't listen to you and they are moving back. So the solution, as we said, is to separate these two counter-moving traffic into one and one. So let's imagine now that we don't have a very thin, do we have a better point? So we don't just have a thin one-dimensional wire, but we have now a two-dimensional flat system. So then we can arrange in a beautiful pattern so that the electrons on the upper side is moving forward and the electron on the lower side is moving backward. So this is exactly the highway system. Because if that is possible, then if the electron hits an impurity, because we said the only possible way the electrons can do is to scatter back, but in order to scatter back, it has to jump all the way to the other side of the lane. This is very, very unlikely. So then, in this case, the electron will simply wheel around or go around this impurity and keep on going forward. So if there's only one type of motion possible for electron, then you will keep on moving forward without dissipation. Problem solved. Except how do you tell the electrons to follow these traffic rules? Here in the human society, we simply build a highway, we pass a traffic law, and then we move that way. So we have to find laws of nature which will direct the electrons to move that way. We have to find some way so that the electrons can follow our will and to display this wonderful pattern of motion. Now, it turns out that this is possible, but it was only possible due to an external agent, which is a magnetic field. So imagine I have this two-dimensional system, and on this two-dimensional system, I put perpendicular to this two-dimensional system a magnetic field. Okay? So a magnetic field gives a sense to the electron. What do I mean by that? So there's something called the right-handed rule. So if the magnetic field, if I put on top of this plane, is my thumb, and which is pointing in the upwards direction, then my fingers are executing this clockwise motion. So actually, if you have a magnetic field, the electron actually feel the magnetic field. So the magnetic field gives them a signal or a direction so that the electrons, all the electrons know that they should move around in a clockwise fashion. Okay? So this is what happens to the interior part of the electron. So for those of you who know ballroom dancing of worlds, it's like they're just going through very simple box steps, going around, and they're not going very far away from each other. But now let's look at the electrons on the edge of the ballroom. What happens to them? Because they cannot complete a full circle, because if they try to complete a full circle, they bump into the wall. So then they have to skip orbit and keep on moving forward. So these are more like the advanced dancers. They know how to make natural turns, reverse turns, and progressive turns. So they all go around. Now they can execute a motion which is going all the way around the ballroom, unlike those in the middle who are just executing a very small circular motion. So this is actually the magic effect of the magnetic field. And it turns out this is possible for the electrons to behave this way. And the discovery of that effect is called a quantum Hall effect. Never mind the words, but basically in essence, it means that if we have an intense external magnetic field, the electrons do know that they can execute this clockwise motion. Now it's clockwise and not counterclockwise because there's an externally imposed direction by the external magnetic field. So it tells the electron to move around in a clockwise fashion, and this way, according to this picture, but the electrons deep inside, they don't do anything. They're just going around in circles. They don't carry any global current from one place to the other. So now, this is called the discovery of the quantum Hall effect made in the 1980s. So this was exactly what I referred to when science and technology parted their way. Here in Silicon Valley, we're obsessed of using the computers, make it ever more powerful computers, and apply them to all sorts of interesting higher-level applications. But science, even though originally scientists, physicists invented the transistor, they feel that there's not much they can contribute anymore because the engineers are so good once they learn the basic principle. So scientists went to explore these exotic phenomena. So why is this called an exotic phenomena? Because it requires a very high external magnetic field of 10 Tesla. Imagine you grab your laptop under a 10 Tesla magnetic field. Now, not only it requires a very high external magnetic field, it also works at very, very low temperature. But this is actually good. Scientists should be left alone. They should be left alone to explore whatever they're interested in. If for the moment scientists and technologists parted their way, this is just fine. But now that we face this crisis, we have to think again whether we can somehow use this effect, but without the extreme condition. If somehow this highway system can work without the intense external magnetic field and without the low temperature, then we can really change the world. Science is no longer exotic or esoteric anymore. What happens? Something's out of power. So we need something that replaces the external magnetic field, but yet something that can give a direction for the electrons so that they will know which direction around the ballroom they should waltz. And that brings us to another wonderful property of the electron, and this is called the spin of the electron. Okay. Oh, no, no, yeah, it is. Oh, okay, good. But it's a different format. We should make it narrower. It's a little bit distorted. It's stretched. But maybe we shouldn't touch it. Okay. Yeah, okay. So basically, it is a wonderful effect. Actually, it was twice, the discovery of which was twice awarded by the Nobel Prize. But it was a little bit exotic phenomenon. It requires very high external magnetic field and very, very low temperature. So scientists need to think about some way so that we replace the external magnetic field by something, but something still be able to give a direction to the electron so that they know which way they have to dance around the ballroom dance floor. And that brings us to the spin of the electron. So actually, it's quite easy to understand basic science because the nature works in a wonderful way that there's always analogies. Okay? When you look at how electrons goes around the atomic nucleus, it's very much like how the Earth goes around the sun. Okay? So when the Earth goes around the sun, there are two types of motion. Okay, one is the Earth's center goes around the sun, and that goes once in a year, right? 365 days. But the Earth also rotates by itself, and the rotation of the Earth by itself gives us the day, 24 hours, and the common motion of the center of the Earth around the sun, it's what gives rise to the year. Okay. So now, for the case of the Earth, actually these two types of motion, the spinning motion of the Earth and the common motion of its orbital center around the sun, so one takes 1 day and the other takes 365 days, does not seem to be so related to each other. But still, the electron has this property which is very similar to that of the Earth. Actually, I don't know if some of you think deeply, look at when you look into the stars. The moon is very different. Okay, so the moon rotates by itself. It also goes around the Earth. So to Earth to the moon is a little bit like sun to the Earth. But the moon goes around the Earth in 1 month. It also rotates by itself in roughly 1 month. So we see in the case of the moon, the spinning motion or the self-rotation of the moon is coupled to its orbital motion. It's actually not an accident that these two periods are the same. Now, exactly what is the reason for it, it's actually a little bit complicated. It's due to something called a tidal force. In the early days, in the molten stage of the moon was molten, there was some tidal force, and the tidal force leads to a coupling between the spinning motion and orbital motion. But anyhow, when we look even in astronomical objects, there's the idea that there's both the spin and there's the orbital motion, and there's a coupling between these two types of motion, at least in the case of the moon. What happened to the electron? Actually, Einstein's theory of relativity predicts that for the electrons, there's also such a coupling between the spinning motion of the electron and the orbital motion of the electron. Okay? So here I have depicted the center of the orbit, which is a proton. Let's take the simplest case of a hydrogen atom. So we have a proton, and the electron has a spin. okay? And the spin actually generates a magnetic field, and if you align all the electrons spinning in a material, that's how you get a magnet. And the spinning motion of the electron actually, according to Einstein, is always coupled to the orbital motion around the atomic center of the atomic nucleus. So how do we understand? Actually, this is much easier to understand why the moon has such a coupling. Because Einstein always liked to play a game like this. He says, imagine that you are sitting on top of the electron. So usually when we look at this picture, looks like like we always had this debate whether the Earth goes around the moon, Earth goes around the sun, or the sun goes around the Earth. But Einstein was always very playful. He says, imagine that you are sitting on top of the electron. Then to you, it looks like, just like we observe, that's why we were a little bit confused early on, that when we observe the nucleus, it looks like it's going around the electron. But the electron has a spin, so it generates a magnetic field. But if the nucleus goes around the electron, it generates a magnetic field. And that magnetic field would tend to align the spin of the electron. So this is Einstein's explanation why, in the case of the electron, because the spin of the electron always generates a magnetic field, and because the proton has a positive charge, when it goes around in a loop, it also generates a magnetic field. And that tends to align them together. Okay? So it is this effect which give us the possibility to completely remove the external magnetic field, because now the spin can give the direction to the electron which way to go. Okay? So this is the idea of the new discovery called quantum spin Hall effect, also sometimes called the topological insulator. So basically, if we remember and put back the fact that the electron also have a spin, in fact, it has two kinds of spin. It can be spinning with a north pole pointing up, or it can be spinning in such a way that the north pole is pointing down. So altogether, even in a very, very thin wire, the electron can have four types of motion. It can be spinning up or spinning down, or it can move forward or backwards. But then you can use the spin of the electron to give the direction to its orbital motion. So in this case, previously, we used the external magnetic field and the right-handed rule to tell electron whether to move clockwise or counterclockwise. But now we're using this wonderful effect called spin-orbit coupling, so that when the electron is spinning up, it is going around the system in a clockwise fashion, and when it's spinning down, it's going around the system in a counterclockwise fashion. So just because of that, we get rid of the external magnetic field. Now the electrons, even though there's no external magnetic field, it knows which way to dance around the ballroom, whether clockwise or counterclockwise. But then, what if the electron hits some impurities? So now in this case, because only the electron, these two, even though they're very close and they're moving in opposite direction, they have different spinning direction. So it's very, very unlikely that when the electron is hitting some impurity, usually the impurity will not be able to flip the direction of the electron spin. That effect is not strong enough. So this type of motion, when electron hits some impurity and goes back, but at the same time turn its spinning direction, is very, very unlikely. So this is forbidden to occur. So as a result, we have this wonderful highway system that when the electron comes into an obstacle, it simply views around and keeps on going forward. So this is actually a moment of very exciting discovery, because it works, the principle at which it works is similar to what was discovered before in the quantum Hall effect, where the electron, due to the external magnetic field, can move around the system, so, like in a highway system, where they separate into different lengths. But now we have the possibility of completely removing the external magnetic field, so the electron how to move in this wonderful new highway system without much dissipation. And if this effect is used properly, maybe we can construct a much, much better chip where your cell phone will last for a month rather than a couple of hours. So now, where in the world do we discover such a wonderful material? So this is a chart that actually, I'm sure some of you here are engineers, and maybe some of you have seen this picture. So just like the chemists have a periodic table for the elements, also engineers and material scientists like to have a chart which organizes and puts different materials together. And this is the way they put things. So first of all, different materials are made out of the atoms. The atoms have a distance with respect to each other, and that's plotted on this axis here. But all these materials, the electrons inside, they move like quantum mechanical waves. So their energy are not, all possible values are possible, so there are always some gaps in the energy. And it turns out it's this kind of gap which makes this laser point possible. Because inside this laser point, there are some atoms, the electrons have some higher energy level, separated by forbidden region and lower energy level, and then when jump from higher level to a lower level, they emit some light of this given frequency. So this chart actually is very, very useful if you want to construct something which takes advantage of the solar light. You should always look at elements of this region, right? Because these lights are compatible with the wavelengths of the solar spectrum. So this is kind of the periodic table of materials. And when you go to most material scientists, this is the thing you see. So now I try to explain to you the excitement how scientific discoveries are made. So sometimes a discovery is made just by a pattern recognition. Okay? So when you look at this picture, there's something very strange. So it looks like all these materials have an energy gap, which I can explain a little bit more, but most people understand they can have an energy gap, and the energy gap tells you the color of the light this material can emit or absorb. But there's one very, very strange material called Mercury telluride, which does not fit this overall picture at all. And this is in the negative axis. It has a gap which is, in some sense of definition, is negative. So now we know that according to this Einstein's theory of relativity, we said the electron can have this spin-orbit coupling, but it will only have strong spin-orbit coupling heavy elements. Not only Einstein predicted qualitatively there's such an effect, he also predicts the magnitude, the rough magnitude, and he says it scales with the atomic number to the fourth power. So by the moment you go to lower part of the periodic table, when the elements are heavier and heavier, the effect of spin-orbit coupling gets stronger and stronger. So when we look at this picture, it's hard to believe that all these materials are topological insulated, this wonderful material, because then we could have discovered them accidentally. But there's one strange outlier, which is not very much used. And actually, at the time we made our theoretical prediction, there's only one laboratory in the whole world that is investigating this, and that's in Würzburg, Germany. So this is this material called Mercury telluride. And just by this pattern recognition, we see, it has a very heavy element, mercury, and therefore, according to Einstein, it should have a very large spin-orbit coupling, and just kind of a bias that it's hard to believe all these materials are the wonderful topological insulator material. And then we said, maybe we try this one first. And that's how we discovered the first topological insulator in the world. So now I need to explain to you a little bit the picture. What do we mean by insulator and metals? So basically, electrons move inside the crystal like waves. And therefore, the waves filter their possible frequency or their possible energy, just like you have a band filter in your radios. Okay? So then the electrons move in these lattice, and they can only have certain range of energy. So these are depicted here, and these are called energy bands. And basically, what you do to the electrons is just like when you fill water. You fill these bottles by water. And if you partially fill one band, then you can kind of tilt the bottle, and then something will start to flow. That's the picture of the metal. Why the metals conduct electricity is due to this picture, that electrons are partially fill one bottle, and then you can tilt, and then something starts to flow. This is the picture of a metal. So if there's a picture of metal, some of you can already guess what's the picture of the insulator. And this will be a completely filled bottle, right? So if the bottle is completely filled, then no matter how you tilt it, nothing is going to flow. You cannot generate a flow by something that's completely filled. So as a result, the electron inside the insulator, they all move around by very small steps around the atomic nucleus. They cannot go in a very large distance. Just like when you tilt the bottle here, it doesn't lead to a flow of the water. So what is a topological insulator in this picture then? So a topological insulator in this picture is more like an hourglass. So it basically has this upper region where it's the allowed energy for the electron, and the lower region, which is also the allowed energy for the electron. But these are the energy allowed for the electron in the interior part of the material. It turns out that when you go to the boundary of the material, then there's some energy that's allowed, and these energies continuously connect The upper one, this is called a conduction band, and the lower one, which is called the valence band. And this is the picture of the topological insulator. It's as if you tied a knot between these two bottles so that you always get a state when the electron, now in this case, the electron cannot flow if you fill the water up to this point. They cannot, in the interior part of this material, it's very much like the picture here, but on the surface of it, they can move freely. So this is kind of the wonderful property of the highway system that we seek after. And now we have a material, and we now need to do some experiments. So by the way, so I'd like to tell you that physics is a very international endeavor. So we, at Stanford University, we were the major contributor to develop this basic idea of a topological insulator, but we also predicted explicitly this material. And now, I told you that there's only one laboratory in the whole universe and in the whole world that makes this material, mercury telluride. It's in Würzburg, Germany, under Professor Lawrence Molenkamp. So we designed the experiment to test. So basically, if you have an ordinary insulator, if you fill ordinary situation here, if you fill the water here, it's a metal. It conducts electricity. When you measure the conductivity of the system, it conducts current. But when you fill the water all the way up to here, it will not feel any conductance. So just the picture I have explained earlier, that no matter how you tilt your bottle, nothing can flow. So if you if you fill the water here and measure the resistance of your material, it will be almost infinite, or it does not conduct at all. But when you fill the electron up to this point, then it can conduct electricity again. So this is the conventional picture, which is valid for semiconductors like silicon, gallium arsenide, and so on. They all have this property. So now what happened to this wonderful new material called topological insulator? As I explained, that it ordinarily has a conduction band and a valence band, but by the time you get to mercury telluride, it has such a strong spin-orbit coupling that it inverts these two bands. So this, what was previously a valence band became a conduction band. What was previously a conduction band becomes a valence band. But after this inversion, you have this state which only lives on the boundary or the edge of the system. So these are the lengths of the highway that we have. And so as then our colleague put the water level up to this point here, they find that the electrons don't conduct at all. So this is this ballroom dancing picture. But if you measure the conductance, there's still some channels of conductance, but they're only on the edge. But furthermore, how much they conduct does not depend on how wide this channel is. And that is kind of a picture that it's really going around in this highway system. So now if we always want in science some kind of a direct evidence the electrons are really moving in this highway system, and that is a recent experiment done by my colleague Catherine Moller at Stanford. Basically, if the current is flowing, it generates a magnetic field. By measuring the profile of the magnetic field, you can actually see how the currents are distributed. And as she took this measurement of the magnetic field, she uniquely infers that the currents are really moving in these tiny lengths and only in one direction. So this is kind of the wonderful discovery of the topological insulator. So we were able to predict, by looking at this graph, we were able to predict which material will have this property. And when my experimental colleagues in a wonderful collaboration worked on it, they indeed find that this is true. So now, we basically solved one problem, but there's still another problem remaining. So I said, this highway system could work from previous principles, but at that time, we need a high magnetic field and low temperature. So using this spinning degree of freedom of the electron, we completely got rid of the external magnetic field. It's no longer needed, but then we still have this fact that this effect still works at a relatively low temperature. So we would like to get rid of all extreme conditions. No more external magnetic field, which we already solved, but also to have something that works at room temperature. So this material was predicted, mercury telluride, has all these wonderful highway property, but still at relatively low temperature. So we need to look for new material. But very recently, we predicted a new material, and we also coined a new buzzword called the stunning, okay? So the element of tin, when you look at the periodic table, its chemical symbol is Sn, not something like Tn, but Sn. So Sn is Latin. It stands for stanon. So if we make a single atomic layer of it and copying the idea, some of you may have heard of graphene, which is a single layer of carbon. So we call this stanin. Stanon because of the element, but something ning means a single atomic monolayer. They actually form a beautiful honeycomb-like crystal, and we predict that in this system, because tin is pretty low in the periodic table, so its spin-orbit coupling is very strong, so we can get rid of the external magnetic field, but also furthermore, it has a very large energy gap. So it has an energy gap 10 times higher than room temperature, so it can work perfectly at room temperature. So this is kind of the new wonderful material, and if it's, the dream is realized, we propose to change the name of Silicon Valley to Tin Valley. So now there are also other materials discovered, but generally, according to this principle that Einstein formulated, that it always happens, this effect happens in heavy elements where spin-orbit coupling is strong. We focused on this region, and we predicted some other material called bismuth selenide, bismuth telluride, and they all have this property that you have a conduction band and a valence band, but then some surface state which kind of connects these two usually disconnected bands together so that the electrons can flow in this surface current fashion. So now how do you really verify this picture experimentally? So this is here the SLAC laboratory comes in. So we can actually do an experiment where you come in with a photon and kick out the electron, and you can see in this experiment that how the electrons behave. And basically, these are the electron states, as we can see in this so-called photoemission experiment, how they behave, and they indeed behave as predicted in this theoretical work, that they connect the conduction and the valence band at a single point, which is like a knot that you tie between these two states. So now this was the experiment that has been done. But the beauty of this subject, topological insulator, is that not only it can be tremendously useful, it's also a laboratory to study interesting and curious phenomena. So these days it gets harder and harder to explore higher energy particles because you need to build a huge laboratory. Here at SLAC, we no longer can afford to build the next generation accelerator because the real estate here is simply too expensive. But sometimes you can construct an analog baby universe kind of situation. So inside topological insulator, there's one particle which we always have been looking for that we never was able to find, and this is called magnetic monopole. So we all know that electron carry a single unit of charge, but all magnets has both a north pole and south pole. We have never ever discovered something that only has a north pole and not a south pole. But on the surface of topological insulator, we predict that you may remember that usually in textbook in high school, it's taught that if you put an electron above some surface, you can generate an image charge. But we predict that if you put an electron on top of topological insulator, the image is a magnetic monopole. It's not an ordinary electron charge. So this effect has yet to be seen, and if it's observed, it was a wonderful way to show how topological insulator is a host to all these exotic particles. Now let me finally explain to you what this magic word topology means. Okay, so this is a concept derived in mathematics, and it's a very, very interesting concept. So you all know geometry as basic, even the Greeks have founded geometry. And as the highlight of their discoveries are the Platonic solids. So let me use those to explain to you. So the Platonic solids are the best example of the beauty of geometry, of this geometrical object. When you look at this object, you all have a deep sense of beauty associated with their symmetry. So they're all formed of this regular polygon glued up together to form a polyhedra so that they all meet at these vertices, they all share edges, and so on. So these are beautiful, beautiful objects, and there are only 5 of them, and this Plato is tremendously inspired by them, okay? But beauty, as derived from symmetry, is also fragile, okay? Sometimes beauties are. And now you have these vertices, and if you misplace them slightly, this beauty of the Platonic solid are no longer there. So because the beauty is only a result of the symmetry associated with these geometrical objects. So then mathematicians have thought about, they have their sense of beauty has evolved, and they want to find beauty in things that are simple and universal. So they ask themselves, if I distort the vertices to very strange corners and randomly add another vertices, are there some things which I can still say that's both simple and universal? And that was discovered by Leonhard Euler, one of the greatest mathematicians of all the time. And it's very, very simple to state. So when you have these objects, you can count how many vertices there are, how many edges there are, and how many faces there are. So if you form this combination, Euler observed that always give you a number of 2. So for example, if you take the tetrahedra, it has 4 vertices, 6 edges, and 4 faces. If you form this combination, give you 2. If you take the cube, it has 8 vertices, 12 edges, and 6 faces. If you form this combination, it also always give you 2. In fact, it doesn't have to be a Platonic solid. You can distort it in any arbitrary shape, and you can try to have look at your soccer ball or anything like that. So as long as it's kind of a polyhedra approximation to the surface of a sphere, this relationship always holds. So this is the moment when the wonderful field of topology was discovered in mathematics. In a way, it's an evolution of a sense of beauty that as you destroy the beauty associated with the symmetry, there's still something that's even more deeper, profound. And this is a quantity which we now call a topological invariant. And that's associated with the idea that it's very robust. No matter how you distort it, this relationship always holds true. But actually not all the time, because I gave a condition that as long as you have a polyhedral approximation to the surface of a sphere, what if you do a polyhedral approximation to the surface of a donut? Then in this case, it's not true. And when you form this combination, it gives you 0. Okay? So in fact, you can have a donut with 2 holes and 3 holes and so on. And Euler discovered that this combination always gives you 2 minus 2 times the number of holes, which in mathematics is called genus. So this is the day when the idea of topology was founded in mathematics. And today, it's the most advanced and admired branch of mathematics. Some of the deepest conjecture are coming out of topological branch of mathematics. And some of you may know that one of the conjecture was only proven recently. A 3-dimensional generalization of this picture called the Poincaré conjecture it's a conjecture in topology and only proven recently. Okay. So now, when we look at in some interesting artworks, you see similar things. So you may know Yuri Milner. He is now a part-time local resident here, famous for early investor of Facebook, and he recently founded a new science prize. Okay, so being something new, he always need to find a differentiator. So instead of inviting the King of Sweden to be the master of ceremony, he invited Morgan Freeman. So I was deeply humbled to receive the prize for the discovery of topological insulator. But my greatest present was that the trophy was actually a topological object. Okay, so when you look at the trophy, it's very interesting. From a distance, it looks like a sphere. But when you observe in detail, actually the North Pole and South Pole are connected. So actually, it's a topological trophy. It's not an ordinary trophy. So now we classify different objects according to how many holes there are, and this is a topological invariant, as I explained earlier. So now if you apply these to all systems, what is the topological invariant? It turns out it's exactly the number of the highway lanes. Okay? So not only you can build this highway lane as one single lane highway, but you can build multiple ways, but the number of highway lanes is a topological invariant. Now, why is this cool and important? Because topological invariance, as I explained, is robust. And this is exactly what we need today in electronics. We need something that's robust, that as I put impurities to all sorts of violence to it, there's something that always stays the same, doesn't change. And that is the number of lanes. And that's the wonderful property of topology as we borrow the concept from mathematics. So just to illustrate, if I have ordinary coating of an insulating surface by a metallic layer, it rusts very quickly. But if you have a topological surface, if it reacts with the atmosphere, it's very, very robust. Even if the top surface may disappear, it simply sinks down a little bit. Okay? So this is the magic for topological insulators. So in fact, diamonds are not forever. They degrade. But these topological surface states are forever. So now what are the applications we already talked about? These are the wonderful highway system we can build in electronics so that we can have this interconnect between the different, not only we can build better chips, we can also connect different parts of chip without almost any loss. Just imagine for those of you who are coming from the semiconductor industry, we went through a transition from aluminum wire to copper wire. That was a tremendous thing. But that, to a scientist, is just some incremental change, aluminum to copper. But someday, I hope that we will make these topological interconnects using these topological insulators, and they will really transmit information without any loss inside the chip. And that actually, to our great surprise, was already recommended by the International Technology Roadmap for Semiconductors. Another application is in the energy space. So our society generates a huge amount of waste heat. Using this kind of material, we can possibly turn waste heat into useful electric energy. Also, the reverse holds true, that if we want to refrigerate something, we can simply apply a current without any moving parts, and it can lead to refrigeration. So these are the things which are still being actively invested as possible application for topological insulator. Maybe something which is a lot fancier is the idea of quantum computing. So these days, you all know that anytime you buy something on Amazon or in any electronic commerce, you need to encrypt your message. And our encryption system is based on the difficulty of solving some mathematical puzzles. And one of the puzzle is called prime factoring. So if I give you a number like 15, it's very easy for most of you here to factorize this into 3 times 5. If I give you 2 huge numbers, it's still relatively easy to multiply them and to get another huge numbers. But if I give you 1 huge number and ask yourself whether it's a composite of 2 factors, a multiplication of 2 numbers or not, like this number which I randomly typed on my keyboard, it's very, very hard to figure out. So the difficulty in solving this kind of problem scales exponentially with the number of digits in the problem. But people dreamed about this idea of quantum computer, which can solve these problems in a split second, in a fashion which we call linear fashion, that it doesn't scale exponentially with the number of digits, but only linearly. And this is the idea of quantum computers, but the problem is quantum computers are also very fragile. But now you see the idea of topology comes in. The topology is the idea that you can build robust things. In fact, when we build anything in engineering, we like to build robust things that are immune to little mistakes. And this is indeed the idea that if we build using this topological material, we can actually succeed in building these quantum computers which can be able to solve problems which was previously impossible to solve. So we're really in a very exciting period in time. And just to put this into a historical context, materials has basically defined our civilization, right? So we have all the important ages of civilization are named after the materials of the usage. The Stone Age, use of stone, and the glory of the Bronze Age is maybe best illustrated by these beautiful bells discovered in China during the Bronze Age, and then we move to the Iron Age and to the Silicon Age. So as we search for the new materials which can carry us to the next generation of the Moore's Law, we are indeed engaged in this exciting search, and that was the story I was going to tell you about today. And this is the topological insulator. It's really was born out of beautiful ideas in mathematics, and it could very well be, indeed has this property that as you hear it, I hope not only you take my word for it, but it should come as obvious that we should, as we go into the bottom layers of the semiconductor device, we should build a highway system for them rather than letting them go in this randomly crowded fashion. And we also have found novel applications, not only in electronics and in energy. But just to make one remark, which is different from everything that was discovered previously. We have discovered many, many useful materials before, but most of the time in the past, they were discovered serendipitously, which is a fancy word of discovering them accidentally. But today, we are trying to save Moore's Law. We try to find new materials, but fortunately, we can use Moore's Law to save Moore's Law. because the tremendous computing power help us to predict and design material properties. And when combined with beautiful concepts out of mathematics, we have a new way and a new path towards material discovery. Thank you very much.
So now we will move to the question and answer part of the evening. Before you ask, make sure that you have a microphone in front of you because we're recording the questions as well as the answers. And with that, I open it to the public. So if you have a question, please raise your hand and someone will bring you a microphone.
Hello. So the 5 materials that you were experimenting with, the stannine and the 4 other ones,
Yeah.
where do you get those? Are they commercially available?
Yeah.
Or?
So like the bismuth telluride, they're commercially available, but not to the level of purity that most scientists want. Mercury telluride, I believe, exists in compound form, but we don't use those 3-dimensional. We need to make thin atomic monolayers. Or few quintuple layers. So these are made by a technique called molecular beam epitaxy, MBE, most of these materials. And the single atomic layer stannine is also proposed to be made in this technique. Basically, you shoot atomic guns to form these structures layer by layer.
Yeah, you mentioned the quantum Hall effect.
Yeah.
And now you get rid of the field and
Yeah.
you change the temperature.
Yeah.
Is there an equivalent of a fractional charge? In the
Very, very good. Yeah. This is the very frontier of the research. People are trying to find fractional topological insulator, fractional quantum spin Hall effect. Not been found yet, but theoretically proposed. Yeah.
Do we have additional questions? Yes.
Thank you. As circuits shrink, you have a problem called electron tunneling. Does this prevent it, or does it bypass it?
Yeah, actually, there are quantum tunneling. Sometimes you can use them for constructive purposes as trying to make on-off switch to these materials, but they are localized near the edge in a very, very thin fashion that it's not the dominant problem in this new vision. There's a question.
Can you predict roughly when this can be a reality? So Silicon Valley become not Silicon Valley anymore?
Well, yeah, I think we are really in a very exciting time, and I think it can go really change the world. Yeah, but there's still a lot of research that needs to happen. But usually the vision has to be clear. And as far as the vision is concerned, it's a clear vision. Then the rest, we just work hard. A lot of times we're searching in the dark, but I'm happy to tell you that we're not anymore. Yeah.
So what is the killer application? Which means you predict which one will be the first one that actually beat up other conventional methods.
So just, well, it may not sound as sexy as you want, but just I told you that just the transition from aluminum wire to copper wire, there was a huge paradigm shift in the semiconductor industry. So I say that even to replace the interconnects by topological insulator will already change the face of semiconductor industry forever.
Hi, 2 questions. One is, what kind of, or do you have current density concerns when you're running these electron highways? How much current can you pack in there? Is there some kind of limit where they start to get so dense they break apart or?
Yeah. So actually, because we're looking for low voltage application anyhow, so current density again is not an important issue. So this also enables you to operate them at low voltage. So.
Right, my second question is, just curious, when do you think, do you have an estimation for when the standing product would, or not product, but
so
material would be made?
So far, everything we predicted theoretically were verified or confirmed experimentally. So I hope that partly because of these, and I know for a fact that a lot of labs around the world are trying it. So once we have this room temperature, dissipationless transport in the absence of any external magnetic field, I think it's really time that it will take off. So far, I think the progress, the concepts are all there, but it's a little bit slow because the temperature is still an issue.
Is this being proposed as a low dissipative interconnect primarily, or are you switching also?
So we try to take a two-pronged approach. So right now in the semiconductor industry, the problem with the interconnect and the dissipation associated with the interconnect is already so severe that it has been proposed that inside the chip, not in far distance, inside the chip, a tiny chip, that they use optical interconnects. But that is really, I think, not a reasonable thing to do, because we have a solution which is all electronic. We're using some new principle of the electron, but still using the electron. The overhead to convert the electrons into photon and back and forth, that I think is, has no future. Yeah.
So I think the previous question touched on this. Would this be useful as a switching mechanism as well?
Yes.
In some way?
Yes.
And would that make the switches smaller, or just simply
smaller
make
and
the dissipation less?
Yeah, exactly. Yeah.
Okay.
Which will solve both the problem at the switch level and at the interconnect level.
All right, thank you.
Is there any hurdles we're going to have to overcome in terms of the lithography and, you know, the building of the circuits that you can comment on?
So I'm of course more a scientist than a technology person, but when we first proposed the Mercury telluride, a lot of people are pretty concerned because it's a material which is not so commonly used, has a lot of properties which may not be all in advantage to us. But stanine and tin looks, it's a very abundant material, it's a friendly material, and we have been making carbon monolayers, why not tin monolayers? So, like the carbon monolayer has been mass produced already. So I think it will come. It's not a showstopper.
Yeah, I'm just a little confused about where you are with the temperature issue. Could you elaborate on that just a tiny bit more?
So with the temperature issue, with the early generation of materials that were predicted, they work at low temperature. There's another material in the arsenide gallium antimonide which has been experimentally confirmed to work above liquid nitrogen temperature, but still low temperature. But stanine is predicted to work perfectly at room temperature, but it's a theoretical prediction. So I'm only making this claim based on the past record of success we had so far. Yeah, it's going to work. Yeah. But it's also tell you that we'll really tell you about things which are happening as we speak. So somebody should do an interesting Google track of this buzzword, stanine.
All right. With that, I'd like to thank all of you for your patience with our projector issues, as well as the patience of our speaker. And one more time, let's thank our speaker and have a safe and pleasant evening.
Thank you.
Excellent. I used to be a Sandy Fetter student.
Sandy Fetter, great.
So I knew a little, but I'm just curious, too many questions, but if you cool it, do the superconductor on the surface?
No, it's a different mechanism. It's a different